So we're gonna jump back in, and we were talking the other day about, let me get a blank sheet. We're talking about conversion of alcohols to alkyl halides. What is up? All right, what was one of the things that, excuse me, that we talked about with this reaction? What is one of the things that you have to do in order for this reaction to take place? What do you have to do to the alcohol? Don't you have to make OH a better leaving group? And then what else do we talk about with respect to the reaction? Like, what type of reaction is it when you are converting the alcohol into an alkyl halide?
I played by the counterfeit, but now it's time to play by my own.
Right, it's a substitution reaction. Then the last thing we said was that you have specific reactions for primary carbons. I'm sorry, not primary carbon, primary alcohols. And then secondary and tertiary alcohols. And I actually went over like what the difference is in a primary, secondary, tertiary. All right, so we did the reaction we did the other day was kind of like this one right here, right? Where you have, we had an alcohol. In this case, it's a secondary. And this method is best on tertiaries, but it'll work on a secondary alcohol. So this will be considered addition of HX to an alcohol, all right? So let's go through this mechanism. We're gonna put the arrows in and we'll answer this question down here also about the primary, like why it's bad, all right? So what's the first step in this mechanism? How do we get from here to here? What process is that? Anybody remember? Don't all speak out at once now. I know it's Friday. We got 25 people logged in and no response.
What's the nation?
It's a proton transfer. How do you think that happens? What would you do? Look at this intermediate right here. Tell me how you got there.
Hear me?
I can hear you.
Okay, sorry, I was on mute. I don't know. But the oxygen would attack the hydrogen bond into the iodine.
Right here?
Yeah. And then that would give, yeah.
So that'll give you that intermediate, right? And then there's an iodine floating around out here. I just don't have it drawn. Right? And it's negative. And then to go from here to here, that's the loss of your leaving group. Right? This is the slow step. Right? The rate determinist step is the loss of leaving group. Right? So how I would just show that here, right? By breaking the carbon oxygen bond. Let me get a better arrow than that. Just breaking the carbon oxygen bond and giving those electrons to oxygen. Right? That'll get me to this carbocation intermediate. Right? That's intermediate is common for these types of reactions, right? You always go through the exact same mechanism, this carbocation intermediate, And then you can see here, you lost water, right? And then now in the next step, the intermediate is just gonna get attacked by iodine. So that would be nucleophilic attack here. Boom. And then that'll get you to your product. So how many steps total were in that reaction? So you had the proton transfer step, which is really rapid. Then you have loss of leaving group, and then nucleophilic attacks. That's a total of 3 steps.
3.
Mm-hmm. So the first step is quick, highly exothermic. Second step is endothermic. And then the last step is also exothermic, right? So your reaction profile will look something like that. Where time is on the x-axis and energy is on the y-axis. Like that, you should have seen that if you watched the video. It should have had a reaction energy diagram in there for the reaction, just to show what's the slow step, what's the fast step, so on and so forth. So this step right here, the formation of that intermediate, that's your rate determining step, right? And this is overall, when you get to the product, you see that you actually substituted iodine for the OH that was over here, right? So it's overall the reaction is a substitution.
Oh, which one was the rate determining step again?
This step right here.
Okay.
Loss of leaving group. In a substitution like this, where you form a carbocation, that leaving group loss is always the rate determining step. All right, so I don't know how much substitution y'all did in part 1, but there are multiple substitution mechanisms, but this one falls under what we call a SN1 type mechanism, right? So SN1 is always going to go through, it's always going to include some type of carbocation intermediate. And then there's other reactions that we're going to look at that fall under different categories, like it's what we call an SN2 type. Do y'all remember that from part 1? SN1 and SN2?
Yes, sir.
All right, cool. That's great. All right, any questions about this?
Not right now.
All right. So let's look at that bottom reaction. I'm gonna leave this. I don't want to erase it because I think I can actually save this as a PDF and then just post it to Blackboard like I did the other day. But the bottom reaction, you can see now you have a different type of substrate. Right? Now this reaction, let's say, is 100 times slower.
Wait, Dr. Russell,
Yes.
are you just showing the second one you just drew? The second one you just drew, you're just comparing it to the one up there?
Yes.
Okay.
So that's what I'm saying. It's 100 times slower. And we're going to answer the question, why? If it proceeds through the same mechanism, it's going to be 100 times slower. So let's look at what happens. All right, so I'm going here. That first step doesn't change. That's going to give me this hydronium intermediate, right? And then that is going to coincide with this loss of leaving group. So now this carbon right here is going to be positive. All right. If we stop right there, can you tell me why it's 100 times slower? think Natalie, I think you hit on this the other day when we first started looking at this.
Is it because the positive is on a primary carbon?
That's exactly right.
Okay, cool.
So this reaction is slower due to the formation of this very highly unstable cation. Right, because a primary cation is not stable.
Would it rearrange to put the positive on the
That's a
secondary
possibility.
next to it?
That's a possibility, but I think a simpler solution to that would be to switch mechanisms instead of going through a SM1
Mm-hmm.
where you go through a cation and lose your leaving group. The iodide would come in and attack directly, whether at this carbon right here, and it would just go through a SN2 type mechanism. Because the rearrangement may cost too much energy.
Okay.
Yeah, you have to take a hydride. If you think about doing like a hydride shift, that will happen from here, and then they'll give you a secondary carbocation. But it may cost more energy to do that than it does for iodide just to attack directly. That's a good question.
Okay.
All right. So again, this method is better suited to secondary, tertiary alcohols, but it's more favored with a tertiary than it is with any of them.
You go back down.
Hmm?
Could you go back down?
Oh yeah. Yeah, you mean back down to here?
Yes.
All right.
So it's slower due to a formation of
Of a unstable primary carbocation.
Dr. Russell,
Yes.
those quizzes that were just posted, is those for the videos
Yes.
you have to watch, just
Yeah.
like last time?
Yeah, the ones I sent out on
Okay. Like I thought it was a test.
Monday. I think. I apologize for not posting the quiz right away.
Okay. I thought it was the quiz. The test. I just wanted to make sure.
No, the test will be up a little bit later. I gotta finish it.
Oh, okay.
It'll be up later today, probably around lunchtime or somewhere like that. All right. Any other questions about anything else about this reaction?
Could you finish it?
Sure.
Thank you.
So the iodine is here. And it's just going to come in and attack your carbocation. So your product will be here, right? Where you substituted the OH with iodine.
Wait, Dr. Russell, where'd the CH2 come from?
Right here.
Oh, okay. I see it when it broke. Okay.
Yeah, when you broke the bond, well, it was already a CH2, and I just drew it out so you could see. I didn't just want to stick the plus charge on at the end of a line like that.
So that one at the bottom, that's the
It's
product.
same,
That's that.
same CH2 is right here.
Okay. Yeah, just wanted to make sure. Okay,
Yeah.
that's that.
All right. Any other questions about this mechanism or this reaction? All right, let's go up to a different reaction. I think we'll do this one first. So another way to make alcohols into alkyl halides is to use PBr3, which is shown right here. Right, so one of the things about this reaction is the stoichiometry. Come on, bro. I'm trying to keep this iPad plugged in. The plug keeps slipping up. There we go. All right. So the stoichiometry of this reaction is 3-to-1, right? So 3 parts alcohol, 1 part PBr3. Right. Once we go through this mechanism that's shown up top, you'll understand why it's 3-to-1. All right. So let's just use some logic. How do we get from here to here? If you just look at what's there, what do you think happened?
Proton transfer.
Well, no, not a proton transfer, because the proton that was here is still here on that side.
Oh, okay.
But can you see that something did happen, right? Can you see now
The
that you have a
nucleophilic
new,
attack?
yeah, you got a new PO bond right here, right? So that means that oxygen had to attack phosphorus. And then you kicked off a bromine, right? Can you see that? So here's the bromine that came off. And then here's the new, let me zoom in on that. Here's the new I'm sorry, the new PO bond right here,
Mm-hmm.
right? So that came from here, right? This oxygen attacking phosphorus. And I think I heard you say that, Natalie, it's nucleophilic attack. Right. And now, what do you think happened going from here to here? And how did it happen? Just look at the
OH.
structures and see what you have. Go ahead. I heard you, Natalie.
It looks like the oxygen leaves as a leaving group, and then the bromine will go in and attack the positive cation left over.
Okay, so let's think about that. Well, you think that oxygen is going to leave first if that's on a primary carbon? Right, that's what we just talked about in this other example we just did. So this method is specific to primary and secondary carbons. Right? So if it's a primary or a secondary, it's probably not going to go through a carbocation. It's probably just going to be direct attack. Because the carbocation that you make is going to be too unstable. So it's going to attack here, and then the CO bond is going to break like so.
Okay, so it's not going to really be intermediate. It's just going to be one step.
Well, this is an intermediate right here, but it's not a carbocation intermediate.
Yeah. Okay.
So this is more of a concerted type reaction. It's still a substitution.
Oh, yeah, concerted.
Right? It's still a substitution. Because you took the Br here and you swapped it with the OH here. Following? So it's still a substitution, but it's a different type. This falls in the category of what's called an SN2 type substitution. right? So no carbocation. All right, questions about that?
Why is this method just specific for primary and secondary?
Because it's a direct substitution, right? So
Okay.
if you all have a primary carbon, you don't want to make a carbocation on a primary. It's too unstable. So you need a method that's like a direct substitution method. That's just gonna attack the carbon itself without having to go through a carbocation.
That SN2 plus what?
No, SN is SN2 type. Sorry about that. So it's a SN2 type substitution. All right. So that particular method you would use if you had a primary alcohol or a secondary alcohol that you wanted to convert. So why do you think look at what's left over? You see this phosphine here that's left over? Why do you think that the ratio of alcohols to phosphorus is 3-to-1? So I used one alcohol, and now this is what I'm left with. I have my alkyl halide that I made, and then I got my phosphorus with 2 other bromines on it. So what do you think? If I have 2 more alcohols left, shouldn't I be able to react it?
Yeah.
Again with this?
Again. Yeah.
Mm-hmm.
And then you'll have the bromines come back in.
Mm-hmm. I'm gonna show you a second. Right, so that can actually react with 2 more alcohols. Right. But you don't start from PBr3. If you have another alcohol, you just start at this compound right here. Let me erase some of this stuff. So what would you do? You would start with, I'm gonna abbreviate this alcohol too because I'm lazy. And it's Friday. Right, you'll start with that. And then the exact same thing is gonna happen. Right, you attack phosphorus, you lose bromine, and then you end up with this intermediate. Put it in a bracket. Right, and then that's what the bromine is going to attack. Hold up. So that's going to attack here at this carbon.
Dr. Russell,
Mm-hmm.
where'd that first bit, like on the left, where'd that come from? No, zoom out.
Hold up. Where did one come from?
Right there to the left.
This?
Yes, sir.
So remember I said the stoichiometry is 3-to-1, right?
Mm-hmm.
I just cut off the tail of the alcohol, but I'm starting with another one of these alcohols up here.
And then you have to do the same for the other one?
Yes. So once I do it a second time, what that's gonna leave me with, I'm out of room. Let me erase some of this down here. What that leaves me with is this. And again, I'm gonna abbreviate that because I don't feel like drawing all those carbons. That plus this, P, OH, OH, Br. Is that right?
Could you zoom out real quick? For the one you just draw, you got it from the second one?
Say that again.
I said the one that you just draw, you got it from the second?
Yes. And then if you notice right here, I got one last bromine left, so I can do it again on another alcohol. But it's not a separate, like it's like in the same pot. You understand what I'm saying? So it's like when I run this reaction in the lab, I add in 3 times as much alcohol as I do PBr3. Make sense or no? Any questions about it? And again, it's a it's a SN2 type substitution.
And this is still halides to alcohols?
Other way around. Alcohol to
alcohols.
Remember I said we were going to do 3 methods. So we did HX, and this is the second method, PBr3. All right, and this this reaction right here, and the one we're getting ready to do was in that last video I sent out. And it showed like the mechanism as well as the energy diagram and all that stuff. All right, any other questions about this reaction? Again, this is addition of PBr3, and it's specific to primary and secondary type alcohols. Why did my E get like that? All right, questions, any questions? All right, let's look at the last reaction under this topic. And it's adding what we call thionyl chloride, or SOCl2, right? And that's what that's going to do is it's going to swap out the OH group here with a chlorine, right? You see when we get to the end. Oh, it's right here. Never mind. Right, it's going to swap out the alcohol with a chlorine, but it's again, the OH is such a bad leaving group that anytime you want to swap it out, you have to make it a better leaving group. Right? And the way you do that is by adding in some functional group to help it to leave or turning it into water or whatever. All right. So let's look at what happens. And this is done with pyridine, which is this compound, this heterocycle right here, this benzene ring with a nitrogen in it. That's pyridine, and it's a base. It acts as a base. Right. So going from the reaction on the left to what you see to the right of it, what do you think happened? What does it look like happened?
The nitrogen attacks the hydrogen on the hydroxide group.
So that is an example of proton transfer, right? Because the nitrogen is picking up a proton.
Yeah.
Yeah, and keep in mind, all of these acid-base nucleophile electrophile reactions, the electrons are coming from nitrogen, right? So you're going to break, I should have this drawn out, but you're actually going to break that OH bond. I'm going to draw it up to here just so I can show the other arrow. You're breaking the OH bond. All right. So that's how we got to here, where the oxygen is now negative. And then you see the pyridine down here with the proton attached to it, and nitrogen is positive.
So is that pyridine with the second mechanism?
Hmm?
Is this pyridine, like, is that with that's the second part of this mechanism?
You mean this side, on this side of the reaction?
Yeah.
Yeah, it's
Okay.
just a side product. But we'll talk more about that at the end, because it actually doesn't stay like that. It's going to give that proton back eventually, but not to OH. But we'll talk about it in a second. All right, so now look at what happens. How do you think I'm going to go from here to here?
Nucleophilic attack.
Same thing, right? The the sulfonyl group is, wrong pen, is going to get attacked by oxygen. And you can see that, right? You can see over here that there's a new SO bond right here, right? So that's kind of a clue as to what happened in the previous step. All right. Anybody not see that? How that happened?
No, I see it.
Right. And the reason it's attacking sulfur and nowhere else is because there's a big dipole between sulfur and oxygen, right? So that makes sulfur partially positive. So that's why it's attacking there. It's not going to attack chlorine, because chlorine already has 3 lone pairs around it. So it's really electron rich, even though it's a halogen. All right. So now so to go from here to here is nucleophilic attack. And then now what you want to do is release chlorine, because what ends up happening is this chlorine ends up being my nucleophile to come in and displace the leaving group. And this whole piece, this whole functional group now is my leaving group.
Why is chlorine displacing the leaving group again?
Because we're trying to remember, this is the goal is to get you here. Right? Mm-hmm. So I want to swap out the OH group with chlorine. That's my goal. Mm-hmm. So that's why the chlorine is that we make from going from here to here, the chlorine that we generate from that's also going to end up being my nucleophile and displacing oxygen. It should be -2, by the way. Right, so how do I go from here to here?
How do you go from where to where?
So from here to here.
What happened? The negative oxygen would make a double bond, and that
I'm
would
going to
push
give a pair of
chlorine out.
electrons here. Yep. And then I'm going to lose one of the chlorines. And that will give me this sulfonyl compound. Is that okay? Anybody not see that? This mechanism is a little bit longer, but it's still it's still relatively short compared to others. So to go from, I'm gonna call this A, to go from A to B is an elimination. Do y'all remember that from part 1? Anytime you eliminate, you always make a pi bond. When you do an elimination, it always results in the formation of a multiple bond, like a pi bond, or a double bond, or a triple bond. In this case, you got a double bond. I'll write it right here. All right, so anytime you're doing elimination, it's going to end up, you're going to end up with a pi bond in the product. All right. The last step is your substitution step. What do you think is going to happen? Let me erase this. I'm just going to draw the product down here. So I don't have to go back to the other end. All right, so I want to get you here. From this step right here. How would you do it?
The chlorine would attack.
Yeah, I just want to kick off the
directly
leaving group, right? So the chlorine is going to come into here like that. And then
the oxygen would.
I'm just going to break the CO bond. Right. Like that. Now, let me talk, let's go back and look at the pyridine part. But see, once you make the product, you're also going to have this as a side product. Right?
Why is it gonna be on the side product if all we're trying to get is?
Oh well, I mean, just think about it now. We're doing chemistry, right? So
Right.
anything that is in the pot, it doesn't just disappear.
Oh, it's like it's still going to be there.
Yeah, what is it? Is it the first rule of thermodynamics that you can't create or destroy matter?
Mm-hmm.
So nothing disappears. Everything is there. It's just crap. We don't need it, but that doesn't mean it's not there. So that's a side product, and then of course the pyridine is still floating around in here. And let me draw that in here. So remember I said earlier that the pyridine would eventually give up that proton, right? It's going to be these two that get together, but then it'll just give the proton to this oxygen. So it'll become an OH, and then pyridine goes back to being neutral. So it'll be a proton transfer between those two. But that's not significant to the reaction. Right. This is my main objective, to make the alkyl halide from the alcohol that I started with.
Oh, did it? Well, what you just drew to the left, did that go there because it, the chlorine broke it off?
Yes.
Okay.
Right. So all this is all trash, right?
Mhm.
You don't need it, but you can't. It doesn't just magically disappear. You just have to. At the end
Right.
of any reaction, you always have to do some type of purification product, and then separate it from everything that you don't want. All right. So that's the last reaction, and I'm not going to dump anything else on you because this is enough. So I'm not going to start something new or whatever. But let's recap though. So we started talking about alkyl halide synthesis.
Mhm.
And I gave you 4 methods. What was the first one? Right, the first one was a Lilly bromination. Is that right?
Yes.
And then we did 3 methods where we converted an alcohol to alkyl halides. Right, we did HX to alcohols. We did today PBr3 to alcohol, and then we also did thionyl chloride. Right, so those are 4 out of myriad of methods to convert or to make alkyl halides, right?
You said 4?
4 total, right?
Oh wait, those. Oh, number 2. Okay, I see.
Is this going to be on the test, Dr. Russell?
Yes.
Okay.
That's why I'm stopping here. I don't want to add anything else. This is plenty. And if you watch the videos for alcohols and alkyl halides, if you've already watched those, then you'll be in good shape. Between that and what we've done in class, you'll be in good shape. All right. Any questions about anything?
On the test, are you going to give us, is it going to be like what we did today where we were drawing the arrows, or is it going to be more like, here's your starting and here's your product?
Nah, I'm not gonna make you do it from scratch. Not right. If we had more time, like if we had done this a couple of more lectures, then maybe. But I'm not gonna make you do it from scratch. You'll have some structures where you have to just put the arrows in.
Okay.
You go to the other part where you made a list. It was in the beginning.
Right here.
Yes.
Yeah. So that's we were talking about the alcohol, using the alcohol as a precursor to an alkyl halide. And we just said that in order to use the alcohol, you got to make OH a better leaving group. That's the first consideration. And then most of those are substitutions where you swap out OH for another halogen. And then you have certain tools in the toolbox, right? If you got a primary alcohol, you're not going to use HX. You'll use a different method. All right. Any other questions about anything else? Nope. All right. We're gonna stop here. I did record this, so I'm gonna upload this to YouTube to our playlist for this class. And the test will probably be posted somewhere between I don't want to say 12 because I got 11 o'clock class. It'll probably be up somewhere about 1 or 2 o'clock, but you'll have until Sunday to complete it.
Okay. Thank you.
All right. I'll see y'all on Monday.
Have a good weekend.
You too.